talk about proving lines are parallel. Yesterday, every one of our theorems and our postulates start out by saying what? If the lines are parallel, then what's true? The angles are congruent or the angles are supplementary, depending on which scenario we're looking at, right? So today, we're going to be talking about proving the lines are parallel. Today, we don't start out by knowing the lines are parallel. We get information that leads us to know the lines are parallel. Okay? That's the key. The theorems and the postulate will look the same as what we did yesterday, but they're actually the converses of them. Instead of starting out by saying if they're parallel, they're going to end up by saying then they are parallel. Okay? So, just a quick review from yesterday and the day before. What do the red symbols mean? Those lines are parallel. Good job. All right? The symbols mean the lines are parallel. What kind of angles are 1 and 5?
No.
Corresponding.
They're corresponding. Now hold on. If you were saying same side, think it through and talk the rest of it out. You're right. They're on the same. Let me try that again. Sorry. You are right that they are on the same side of this transversal. But what's the next part of same side? Interior. Right? Are they inside the parallel lines? No. So that's, you would start out by thinking, hey, these are same side, and then when you continue saying interior, hopefully you would realize, wait a minute, they're not inside. Okay? So they're not same side interior. Now, they're not interior at all, so that rules out alternate interior, doesn't it? So then we go back to, are they in the same position? And 1 is top left and 5 is top left. So they are corresponding. That's correct. Okay? Corresponding. So you might, in your notes, you have this picture there. You have nothing else there. And this is what I was saying about the sub coming in, expecting him to teach from my notes. You guys don't know it, but I had Tuesday, second half of the day, I was part of a professional development opportunity. And so I had a sub for 5th and 6th period. Well, they says he didn't teach us very much. And he's supposedly a math teacher, they said. Well, it's hard to take someone else's notes. What does someone else get from that page on there? They don't know what I was thinking about, why I put that page in there. I want to put that in there to review what we've been talking about to make sure we understand where we've been. Okay? So, Megan, if I pick on you for a minute, can you name a pair of same side interior angles? 3 and 5. Does anybody agree with her?
Yes.
Yes, very good. 3 and 5. They're on the same side. We move these squares out of the way. They're on the same side of the transversal, and they are inside these parallel lines. Okay? Very good. One pair, Emily. Can you name me one pair of alternate interior angles? 5 and 4. Do you agree with her, Nick? Yeah. Nice job. That is correct. 5 and 4. They're inside the parallel lines. They're on opposite sides of the transversal. They're at opposite intersections, right? 4 is up here at this intersection. 5's down here at this intersection. Yeah. Louder, please.
What are those called again?
Alternate interior. So AIA. I'm sorry. I started to say this and then I stopped. I got distracted with my sub. But from this page, which you could be writing on this page, is alternate interior and example, and write that down. And you could write same side interior, or SSI if you want. And then give the example we used. What was it? 3 and 5. And then corresponding. What was our example there? 1 and 5. Okay? So you can make a list of those that way. You could rename them all if you want to go further. Make sure, if you're sitting here thinking, oh, I think I got it, but I'm not sure. Is there anybody in that position right now that'd like to ask me what kind of angles a certain pair is up there? Does anybody have any questions that you're thinking, well, I wonder, are 4 and 6, whatever? Yes, Paul?
2 and 7.
2 and 7. Nice job. We actually don't have a rule on those, but in our homework, we talk about that. I don't know if I assigned that problem this year or not. In our old textbooks, we have this rule. We can prove that 2 and 7 are congruent if those lines are parallel. They're on opposite sides of the transversal, aren't they? And they're outside the... No, they're on opposite sides, so they're not same position. 2 is top right, 7 is bottom left, right? So they're actually called what? Nice job, that is what they're called. Well, just some textbook authors approach things a little differently, and our last textbook took time to prove that that was true, that these are congruent, and so they also have an alternate exterior angle theorem. Remember, a theorem is a statement that can be proven to be true, and if they want to take time to prove something's true, they can make it a theorem if they wanted to. Just, I think the traditional textbooks don't have it in there. Okay? I'm not an expert on traditional geometry, and okay, I can only tell you from my experience when I was in school and the books I taught from. Okay? So, anyway, they are congruent, and we can prove it using transitive property. And I think one of the questions in the homework asks you to prove that. They walk you through it, I think, but it can be done. All right. Any questions? Any other questions on this slide? Okay. Nice job. Did someone have one? Okay. Now, you see this picture? What's it saying about angles 1 and 2? Would you not put your shoes on the seat, please? They are corresponding. Nice job. They're in the same position, aren't they?
Yeah.
What do those little red lines mean? But you notice they're exactly the same number of them in the top as there is in the bottom? It means they are what? Louder, please.
Congruent.
They are congruent. That's right. You have to understand when 5 people are trying to answer me, I can't always hear what you're saying. Okay? They're congruent. And so that's what that means. When you see symbols like that, or if I see symbols like this, that means those two are congruent. But they're different marks, so are they the same as this angle here?
No.
No, they're different angles. They're not congruent to each other, but they are congruent to these two. Okay? That's what those symbols mean. All right? Now, does it say lines S and T are parallel? No. Doesn't say that, does it? There's no symbols there. Okay? And so that picture, which you have on your paper, right, goes along with this postulate. It's called the converse of the corresponding angles postulate. And what it says is if corresponding angles are congruent, then the lines are parallel. Now, just like yesterday, I've reworded these a little bit. This is not exactly the way it's worded in the book. I'm trying to take out the double talk type language and all the extra stuff and just try to get to the basics for you. If we're looking at corresponding angles, if we know they're congruent, then that means those lines have to be parallel. That's what this postulate says. And it's the converse of what we learned yesterday. Okay? If corresponding angles are congruent, then the lines are parallel. Got that written down already? If the corresponding angles are congruent, then the lines are parallel. Okay, the next one has a picture of 2 lines again. What kind of angles are we looking at this time? Alternate interior. What's it saying about them? single mark on them, meaning they're congruent to each other. And what do you think the converse of the alternate interior angles theorem is going to say?
If corresponding angles
Listen.
are congruent, then lines are parallel.
Okay, what were you saying, Cody?
And if corresponding angles are alternate interior, then lines are parallel.
Okay, you're close. You're kind of mixing it up with the first one. What kind of angles are they? Alternate interior, good job. And they are what to each other? Congruent. So you're going to say if alternate interior angles are congruent, then the lines are parallel. Okay? Again, it's the converse of the one we talked about yesterday. Yesterday we started out knowing the lines are parallel. Today we start out knowing the angles are congruent. What's that name? Parallel. Okay, sorry, I couldn't hear what you were saying. Parallel. I'd like to pause for a moment. I don't want to say anything else. I'd like you to think in your group for a minute, see if you can write this down without peeking and looking in your book. See if you can come up with the converse of the same side interior angles theorem.
No.
Thank you for that time to wander around, and thank you. Not everybody mastered right on this, and that's okay. It's new. If you guys were expected, if I expected you to know all this, then what would be the point of you being in here? Right? It's a learning process. And sometimes that learning process is talking things out. I could just tell you what it is, but then you never have to stop and think about what it's saying. If I make you think about what it is, then you're thinking about what it's going to say a little better. What kind of angles are in this picture? This picture up here.
Supplementary.
They are same side interior, and you've noticed they're what?
Supplementary.
They're supplementary, which means they do what?
Equal to 180.
Yeah, they add up to 180. Okay? So if these two angles add up to 180 and they're same side interior, then we'd start out by saying what? If
the same side interior angles equal up to 180,
then
the lines are parallel.
okay. I like to try to avoid saying equal. At least if you say equal up to, it implies you're adding, but if you just say they equal
The sum.
180, then it kind of sounds like you're saying each angle is 180.
Equal to the sum.
Yeah. If you say they add up to or they have a sum of, it's even better. In this case, we're just going to say if the same side interior angles are supplementary, then the lines are parallel. Now, if you wrote that, you're good. Don't rewrite it. If you wrote it a little differently, then maybe underneath there you should write it in and put an asterisk next to it to make sure when you're studying you remember that that's what we want to remember. Yours might be a little bit different from that. Okay? But remember, did I tell you this is exactly the way it's worded in the book? No. So do I care that you know exactly how it's worded in the book? No. The only reason I mention it's not worded the same is in case you're looking at the book later, or if somebody's watching this online and saying, hey, that's not what that theorem says. You didn't put this in there, and you didn't put that in there. I don't really care what they put in there. This is what I want to make sure you get out of this, okay? All right. Anybody not done copying it down? Moving on. We have a couple more theorems here. They don't have names to them, do they?
No.
You know, it's difficult sometimes. They don't have names, and sometimes they're long-winded. What do I mean by long-winded? They say a lot of stuff, right? This one talks about two lines are parallel to the same line. So you see we have in this picture lines R, S, and T. So if two of these lines are parallel to the third line, then they are parallel to each other. So if I knew that R is parallel to here too. This kind of follows that common theme that we've had a property about and a law about. If R is parallel to S and S is parallel to T, then what do you think is also true?
R is
R is parallel.
R is parallel to T, that's correct.
Oh my
Yeah.
gosh.
And which property does this look like? Starts with a T.
Transitive.
Transitive property, nice job. Which law does it look like? Law of syllogism. Okay? They're all very similar. Okay? Now, I was trying to think of if I left the words in the plane out on this one, or if it doesn't matter. I can't think of a situation where it matters, so it's probably not in there. And you don't know what I'm talking about, but that's okay. The next one. Here we put in a plane. Let me move this up. There you go. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. We have to throw the words in a plane in this. And I'll explain why as soon as you're done copying it down, and you can listen and watch, and we can talk about things a little more. Okay? It'll be harder to see at home because I'll be using the room to help you see it, but we'll do the best we can. Remember that little box in the corner doesn't mean right angle. What does it mean? It doesn't mean that. It implies that, but it doesn't mean that directly. What does it directly mean? Starts with a P. Perpendicular. Okay? It doesn't mean it's a right angle. Now, what does perpendicular mean? Like it's a right angle. Okay? And a right angle means that its measure is 90 degrees. So we can get there by knowing it's perpendicular, but the symbol doesn't mean right, it means perpendicular. Okay? So, we have to throw the words in a plane because you see the line in the corner of the room here that goes vertically up and down?
Nope.
Okay? Where the two brick walls or block walls come together, it forms a line there. Do you see that?
Yep.
Okay. Do you agree the line along the ceiling in the front wall, that strip there, that forms a line there also?
Yep.
Do you see how those two lines meet like this?
Yep.
They're perpendicular, aren't they?
Yep.
Okay? Do you see how the line in the ceiling against the windows and the line on the front wall in the ceiling, they're like this, aren't they? Do you agree they're perpendicular?
Yep.
Okay? So we have, sorry, I got to think this through a little bit. I tricked myself up. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Okay, that's what I missed the word parallel. In a plane, we're saying that if these two lines are perpendicular to this line, then they have to be parallel to each other. But the two lines I just described were both perpendicular to the front wall, weren't they?
Yep.
So the corner of the room now, looking back at the corner of the room, and then along the ceiling with the windows, they kind of look like this, don't they? Are they parallel to each other? No, they're actually perpendicular to each other, aren't they? So that's why we have to say in a plane. If we talk about in space, if we add that third dimension, a plane has two dimensions, length and width. If we add height to that, length, width, and height, we have space. And in space, this rule doesn't work. Okay? It could work, but it would only work if they were all in the same plane within that space. Okay? It's not going to work if we use more than one or more than two dimensions. All right. Any questions on this one? These are not, these two here, they're not ones that you're going to have to absolutely memorize. Not at all. Okay? I allow you to use your notebooks on the tests, on your quizzes. If you have to know these, they're there in your notes. You can look at them. Okay? You guys sometimes ask me on a test, what lesson is this from? And I don't always remember that either. So do a good job of identifying what's in what notes. Okay? Your I can statements help you know that, don't they? What's our I can for today talking about? Without looking. Can anybody do it without looking? Doesn't have to be perfect. Just give me some hint what we're talking about today. Finding that lines are parallel, right? I didn't hear your first words. Is that close to what you said? Proving lines are parallel. That's what we want to do today. Proving lines are parallel. Using all the information that we've learned before, and now we're learning a couple new ones. Two lines parallel the same line, they're parallel to each other. Two lines are perpendicular to the same line, they're parallel to each other. Okay. What time is it? 8:40. Okay. Let's do this real quick. I'm not expecting a single one of you could do this proof yet. I'm not expecting that all of you combined working together could do this proof yet. Have we done any proofs together yet?
Yes. No, we do.
Not really.
In our homework class.
What we have done is I've given you all these statements, right? On this side. And then you put in the reasons. Do you agree? But all of these statements so far have been what kind of work? Solving equations, right? I didn't hear what you said. Yeah. Yeah, mathematical is solving, right? We're just solving equations. Today, we're going to go a little bit further into that. Okay? So, let me erase this. Again, I'm not expecting you to be perfect at this. I'm going to spoon feed you on a lot of this a long ways through. Okay? We're going to take our time. At some point, I'm going to ask you to understand some basic, simple 3, maybe 4-step proofs, and you're going to have to be responsible for a few of them. But not a lot of it. Okay? Most of it's going to be, I give you some statements over here, and then you give me the reasons for them. Or maybe I give you a couple statements, I leave one blank, and give you the reason. You have to tell me what that was. So I'm going to help guide you through it a little bit. But this is the first step, me doing it with you. Okay, so what are we given here?
S is congruent to R, T is congruent to R.
Close. What's that symbol mean? It doesn't mean congruent. It means,
It's just look this down.
what's that symbol right there mean?
No, I learned it yesterday.
Another thing is, segments can be congruent, angles can be congruent, but lines never end, do they? So lines are never going to be congruent. Okay? Perpendicular, that's what that symbol means. If you didn't know that, you should write it down somewhere that symbol means perpendicular.
I knew that. I knew it.
Okay.
Upside down, I forgot it.
Yep, that upside down T. In fact, to be honest, I think that's what that is. I didn't want to search for a perpendicular symbol through my math stuff, so I think I just went off the side, made a T, and rotated it upside down and cloned it, and used that here for my my symbols. It means perpendicular. Yeah. This symbol means perpendicular. So I ran out of room there, scrunched it together. Perpendicular. Okay? So, the lines S and R are perpendicular. The lines S and T are perpendicular. And we want to prove that S and T are parallel. So in other words, we want to prove this theorem. Okay? That's what we're doing. We're proving that theorem. Remember that the theorem are statements that can be proven to be true. And we're going to take a moment to do that. Okay? Let's speed this up. So, first thing I always write with a marker. I always rewrite what they give me. I know that was true?
The definition of perpendicular.
Could be, except in this case, they just gave me that statement exactly right there, right?
Given.
Yeah.
Put given.
Yep, given is what we put there. Good job, Cody. Oh my goodness. I said right in your name. I turned given into Cody. Kitty. Giddy. Yeah, that's what I was going to write. Okay? So it's given to me. Now, why did it give it to me? Well, what's labeled in our picture? Two angles, right? What are they? Angle 1 and angle 2. What are they? What kind of angles are they? Well, the lines are perpendicular, making them right angles. So, we're going to say, I'm going to go real slow about this. This is what I've been talking about. It doesn't lead directly to an angle. It leads to this statement here, that angle 1 and angle 2 are right angles. Okay? And Cody, you know the reason for this. Don't overthink it. Think about what you've already said.
Oh, definition
Definition
of perpendicular.
of perpendicular. That's the reason. We were told right here those lines are perpendicular, and the picture shows, sorry,
Okay.
the picture shows angles 1 and 2 are those angles, and so those angles are right angles. And that's by definition of perpendicular. Okay? And if you want, you can use that symbol to say the long word of perpendicular.
I was about to say corresponding angles.
You're about to say that?
I was about to say corresponding angles of parallel lines are equal to.
I'm excited that you're about to say corresponding angles, but let's do one more thing first. Back on page 99, we were told that right angles are what? Right angles come from perpendicular lines. They are 90 degrees, but what's special about all right angles? On page 99. What's that? Yeah, that makes them congruent. You're exactly right. They equal the same number. That number was what? Right angles? What's that? 90 degrees. Okay? It was 90 degrees. And so, the reason I know this is true is because of that theorem, which doesn't have a name, that simply says all right angles are congruent. Okay? I don't know why this continuously gives me a little dot once in a while. I must get too close.
So could we name the theorem of right angles?
We could, but by the time you said the theorem of right angles, you might as well just said right angles are congruent.
Does that really thing mean parallel?
Means congruent. This symbol here means congruent. Okay? It's an equal sign with a squiggly over it, means congruent. Now, we just said those angles are congruent. And Cody, you told us they're what kind of angles?
Corresponding.
Corresponding. They're corresponding angles. And so my next step is going to say that line S is parallel to line T because of the converse of the what? No. What are we learning today? What kind of angles are they? Corresponding angles.
Converse of the corresponding angle.
Converse of the corresponding angles postulate. Converse of the corresponding angles postulate. Can't spell today. converse of the corresponding angles postulate. Once I've proven those angles are congruent, then I know those lines have to be parallel because of that postulate. That postulate says if the angles are congruent, then the lines have to be parallel. Okay? Now here's my philosophy. Some of you will catch on to this very quickly. Some of you will need a lot more practice. Okay? Many of you, when we're done writing proofs, are going to regret that we're done. Because you're going to realize, wow, these are all pretty straightforward, pretty easy. I get these right every time. Okay? Others are going to be glad you're done, but most of you are going to be a little bit sorry we're done with proofs. Because they aren't that difficult if you continue. But my philosophy is I need to show you this every chance I can. The more you see it, the easier it will become for you. Cody?
I was going to say, should you do an example, one that has required substitution?
That required substitution?
Yeah, it's maybe when you're doing one statement, you can use substitution.
Yeah, we've used that a lot. We're kind of moving away from the mathematical side, and we're moving into the more the logic side. Well, because I know this is true, what does that tell me? Well, that tells me this is true. What does that tell me? Well, that tells me those angles are congruent. Well, why was that important? Because if I know those angles are congruent, that means that these lines have to be parallel. Okay? So, you remember we talked about deductive reasoning? We're leading to that deductive reasoning now a little more abstractly than it was when it was an equation and you already knew how to solve equations, so this side was very easy for you.
I was just saying that I know there are statements and reasons ones for various substitutions.
Absolutely. Absolutely. Yes? Okay. My only point is, Cody, we're weaning away from those now. There's going to be less of that and more of this. Okay? So, you know what your assignment is? It's on the next page. I don't know what happened to that page.
You can just write it.
Here it is. Okay? So we have odds to 23, that's 12 problems, and then add number 24. We have 13 whopping problems, not a lot of time, but I'll give you a little time tomorrow before we take notes on tomorrow's stuff. Okay?